And we're back. Welcome from your weekend. I hope it was restful and you are staying safe, practicing proper social distancing. As I understand, for many states around the country, they're under stay-at-home orders, so hopefully everyone is in a warm, comfortable place with people that you know and love. Nonetheless, we will continue on with our discussion of the data plane. First, some administrative information. Homework number 3 is on the blackboard. It is due the evening of Tuesday, 31st of March, at the usual 1 second before midnight, 11:59 and 59 seconds. So where we last left off, we talked about how IP addresses are handed out. And as we discussed, these addresses are allocated by subscription blocks of addresses, and this Internet Corporation for Assigned Names and Numbers, or ICANN, is the organization that is responsible for managing these addresses, but they're also responsible for managing domain names. And so if your last name, for example, was McDonald's, and you decided that you wanted to start a restaurant called McDonald's, and let's say you bought an IP address called mcdonalds.corp or .inc or IT, well, I'm sure the hamburger restaurant would have a problem with that. And if you were, by some feat of performance, were able to acquire an IP address, rather a domain name, with McDonald's in it, I'm sure the McDonald's Corporation would take you to court, and there would be a stretched out court battle as to your rights to be able to use the name. Now, ICANN, in that instance, would be the one that arbitrates who the name should belong to. Nonetheless, we have this icon.org, and you can actually go there and get blocks of IP addresses. Okay, so let's continue on. So we talked about this idea that there aren't enough IP addresses to go around, because when the internet was first designed, there weren't that many hosts attached to the network. Fast forward to today, well, typical person has quite a few processors, whether explicitly in the form of a laptop or tablet or maybe a smartphone. You also have a bunch of computers in your various embedded devices. There are washing machines that are Wi-Fi connected. There are now smart light bulbs that are Wi-Fi connected. And so if the typical home can have more than maybe a dozen or more different computers, hosts attached to the network, you'll quickly run out of IP addresses using this dotted quad representation that we talked about. So when you subscribe to Internet Service Provider, you receive only a single IP address. And this technology, Network Address Translation, or NAT, was developed in order to share this singular IP address among multiple devices, each one of which needs its own IP address. Now, some of you have looked at the IP address associated with your laptop. So, for example, if you were to pull up your IP address now, whether you're at home on your home network, or maybe when you were on the campus network, your address would be of one of two different forms. It would have an address that looks like 10.0.0.x, where X would be some number. So it could be 10.0.0.112 or 10.0.0.1, 10.0.0.2, and so forth. Now, going by our CIDRized IP addressing, if you had a 24-bit network mask, that means the first 8 bits, so that's the first 8 bits, that decimal number, that's the second 8 bits, that's the third 8 bits, for a total of 24, excuse me, for a total of 24 bits representing the subnet. So as such, that's the subnet, and that subnet has a special name. It's called a private domain. Now, this private domain is used for private networks, and that means everything on this side of your cable modem or your router that you get through your service provider in the home environment is private. No one on the outside, on the internet, rest of the internet, can see any of the devices specifically, one by one, uniquely on the private side. So this is private. Every device or host that has an IP address on this private domain, this private subnet, as it were, no one on the outside can address them. And it's the NAT, Network Address Translation, the NAT box's responsibility to map between these private IP addresses and that single public IP address. And so everyone, let's say you have Netflix, maybe there's a server hanging on a data center in a cloud owned by Netflix. Now, when you do media streaming, this Netflix server instance, it can actually see your publicly facing IP address. So this is public, and it's a single IP address, and this is private, that represents private domain. Now, the private domain isn't just a 10.0.0.x IP address. There's another form of your private domain, and it is 192.168.x.y. That's the other private domain. And as such, you have 16 bits here of address space that you can tinker with. And so this subnet specifically is another form of private domain. And so here we have your public internet and your private domain. And so all of the datagrams that leave the local area network, so this is your local area network, this is the wide area going out to the internet. All the datagrams that leave your local area network are going to have a single source IP address, and that's going to be that singular IP address that was assigned to you on the publicly facing side of the NAT box or the NAT function. And so you have datagrams that when they're initiated by hosts that are on the private network, they're stamped with their IP address. So this NAT box is going to map or associate datagrams that are sourced on your local network to this IP address, this public IP address, in some fashion that we'll talk about in the next few slides. Okay, so how do we do that? Well, the only other piece of information you can have to make things unique as it pertains to this IP address that's publicly facing is using the port number in the translation layer, right? And so a combination, as we'll see, of this public IP address as well as a port number is going to be used to map and identify every unique IP address that you can have, and there are 256 of them that you can have in this private domain. Now, of course, there are 256 address on the private domain or on this private subnet because you have this 8 bits, right? It's 32 bits total, so there's 8 bits that are the host portion, and that means you can have 2 to the 8 power, which is equal to 256 different unique hosts that are on this 10.0.0 network or subnet. Okay, so the motivation for this has to do with that there's just one IP address that you use for the home network, right? So as far as the outside world is concerned, that you only have a single IP address. And you don't need really a range of IP addresses from the service provider. All you need is a single one to identify that entry point into the home network. And so, moreover, that the devices that you have on the home side or the private part of the network, the IP addresses can change. So let's say, you unplug this one and then you plug it back in, and all of a sudden now the host portion is 4. Or maybe, you add an Xbox, you add something, and maybe that host number portion is 6. And then you unplug your Xbox and you plug in a smart TV. Smart TV becomes 6, and now you plug back in your Xbox. It's now 10.0.0.7, for example. You take your laptop, you open it up, it gets an IP address on this 10.0.0 subnet from a DHCP server running locally. And then you close this laptop, and you bring it to school, then you bring it back home, open it back up again, it gets a different IP address. So certainly on this private subnet, this private domain, the addresses of the devices in this local area can change without notifying the outside world. From the outside world, well, it's the same static IP address. From the perspective of the inside on the private network, these IP addresses can change. The other motivating factor is that certainly you can change service providers. Now, if you change service providers, you shouldn't have to change the addresses of all the local devices in the local network. So what does that mean? Let's say you switch from Comcast to Verizon. All of a sudden, this IP address is going to change. It might be 164.22.19.3, for example, when you switch to Verizon. But you started out on maybe Comcast and you got this 138.76.29.7. You shouldn't have to change any of these IP addresses on your private network just because you switched service providers. Moreover, if you're using longest prefix matching, which you are, if you owned this IP address, so let's say you went to ICANN and you got this IP address, it was yours, well, you could certainly move with it, but in the case we have a service provider, they're actually giving you a particular IP address. So if you leave your service provider, you're invariably going to get a different IP address, but you shouldn't have to reconfigure all the machines on your local network, your home network. Okay, so let's take a look at what the NAT router or the NAT box has to implement. Any datagrams that are going outbound, so you start with a datagram inside the home network and you send it to the outside world, to the internet, it's going to make a replacement. So this 10.0.0, 10.0.0.x address, it is sent to the NAT, and now you must replace this IP address. And moreover, not only does it have its internal source IP address, it also has some port number, right? Because it implements all the correct packet headers for each of the layers, including the transport layer. So you have a port number and you have a source IP address from this 10.0.0 subdomain or subnet. So we have this information when you're sending data outgoing. So what happens is you now have to replace the IP address, and let me remind myself, 138.76.297, 138, and I'm forgetting already, 138.76.297, 76.297. So what you're going to do then is when this datagram gets sent in the outbound direction from the private to the public, it's going to rewrite the IP address, replacing this 10.0.0x with 138.76.297. In addition, it creates a port number, and it's going to rewrite this port number to be whatever port number was selected for the outbound side on the public side. So it takes that entry, it records it, and it uses that mapping. Every time you see this IP address and port number, you're going to replace it with this public IP address and port number. Okay, so this is going to happen on the outgoing side, and the converse happens on the incoming side. What happens on the incoming side? Well, on the incoming side, you have your public side of facing the internet, and then you have the private side and all of your devices on your home network. Now, on the public side, well, what happens? It got a datagram, and from the perspective of the public internet, it had IP address 138.76.297 with a certain port number. So when it sends back the response, the destination is going to be 138, that public IP address, .76.29.7, and the destination port number is going to be that same port number that it got when it came on the outbound side. So now this NAT is going to look up that mapping, and it's going to rewrite that datagram and forward it along that output port on this private subnet 10.0.0. So what does it write? It says, aha, this IP address and that port number, it was mapped to this 10 address and that port number. So it's going to write that 10.0.0.x as well as that port number. So now when it has that 10.0.0x destination IP address that it's rewritten, forwards that datagram with the IP address and port number for the private side, and then it sends it down the wire and makes its way to the correct machine. Okay? So the thing to remember in this table, the so-called NAT Translation Table, every source IP address and port IP address on the private side is mapped to some public, to that same public IP address and new port number. And this pair, this mapping, is used both on the outbound side as well as the inbound side. Okay, so let's see this in action. Again, we have the private side of the network on the right, your right, and we have the public side on the left. Public IP address is 138.76.29.7. And we have the 10 network, 10.0.0.x. So this is host 4 on the 10.0.0 network. This is host 1, host 2, and host 3 on that same 10.0.0 subnet. So our subnet mask is 24 bits for this private domain, this 10 network. Okay, so let's see what happens. We start out, and let's say this top machine, host 10.0.0.1, is going to send a datagram outbound to public IP address 128.119.401.86, and it's going to contact port number 80. Now, we all know at this juncture that port 80 is reserved for hypertext transfer protocol. So this would be a browser or web client, hypertext transfer client that's trying to contact an HTTP server. So the source IP address in this datagram is 10.0.0.1. The port number, for example, might be 3345, and the destination address is 128.119.401.86. Destination port for HTTP is port 80. So it sends it to the NAT box. The NAT box then adds an entry to its table, and it selected port number 5001 for the outgoing entry port number, and it included IP address associated with that public IP address that's facing the public internet. So now that datagram would get rewritten, replacing that IP address 10.0.0.1 with 138.76.29.7, and replacing port 3345 with port 5001. So that rewritten datagram is pushed out onto the network and gets to that maybe data center Netflix. Okay. An entry has been written in the NAT Translation Table that has on one side the wide area address and port number, and on the LAN side of this table has the private domain IP address and port number. Okay, so this entry is going to be used to look up how it's going to rewrite for subsequent outgoing packets as well as for incoming responses, incoming direction, or the inbound direction. So let's take a look at that. So let's say the web server sends back a response. So now the source IP and port number is 128.119.40.186, port 80. So that might be the HTTP server's response back to that client on that private subnet, the private domain. And the destination address is going to be 138.138.76.29.7, port 5001. So you notice, just in typical fashion, when you're sending back the response, the destination is going to be what was the source when the request came in. So this public web server here in Netflix data center, it has no idea that it's a machine from your private domain that's sending this request. All it thinks and knows is that source 138.76.29.7, port number 5001, originated this datagram. So when it sends back the response, the destination address and port number is going to be the same as that source address and port number that happened on the outbound side going out of this private network. Okay, so let's take a look at this. So we have this response message. The destination address is 138.76.29.7, port is 5001. So it arrives at the input port of this NAT box. This NAT box sees this destination IP address, sees that port number, and it says, aha, well, I know the destination address. That's my IP address. Okay. Which port number is it? Which destination port? It's port 5001. So it consults this entry and it says, okay, well, that corresponds to private domain IP address 10.0.0.1 with private domain port number 3345. So it rewrites the IP address inbound to be 10.0.0.1 and the port number to be 3345, and it forwards that datagram with that new IP 10.0.0.1 with port number 3345, sends it out that port, output port for the NAT box associated with its private domain, and then it reaches the correct endpoint. Okay. So the NAT router changes this datagram's destination address from the public-facing address to the private-facing address, and it changes the port number 5001 to that private port number 3345. Okay. So the port number field, recall, is 16 bits long, so that means you can have 65 or just over 60,000, which is really 65,535 different devices on your private network. Now, of course, the 10 network can only support 256 hosts, but as far as the port number is concerned, you can have 65,535 different connections coming in to this single IP address, because you can have 65,535 different choices, so 65,535 different choices for that port number, right? So that means you can have 65,535 connections between some host on the inside on your private network and some host on the outside. Okay, but this NAT idea is very controversial because it's performing functions that don't really deal with layer 3 functions, right? It should only process up to layer 3 when you're dealing with routing in general, but it's changing things like port numbers, which is a layer 4 transport layer. It violates this end-to-end argument about what it means to have a network layer and a transport layer. Moreover, once we switch to IP version 6 in full force, you're going to have so many IP addresses, you're not going to need to use NAT. And where does this NAT exist? When you buy this box in Best Buy that you used to call a router, right? That router has a bunch of things in it. Well, certainly this box has a routing function. It can store and forward datagrams. It also, so it does routing. You might buy it from Best Buy for about $100 to $300, depending on the features. It also has DHCP. This DHCP allows you to dynamically assign IP addresses to hosts that join your network. Okay. You also have, in many of them, DNS, the ability to resolve names. Your local DNS some of these better routers can run in them, these devices you call routers. We also have NAT. So NAT exists in what you call a router box that you might buy from Best Buy for maybe $100 to $300. So when you say you're buying a router, you're not really buying a router. You're buying a device that has a router, it has DHCP, it has DNS, and it has NAT, as well as something we'll talk about when we deal with the link layer, something called a switch. Okay. So it's a lot more than just routing that happens in these little boxes that you buy to get home internet connectivity. All right. So let's take a look at software-defined networking. And this SDN is a generalization to add programmatic control to the types of capabilities that would be set or controlled or implemented in your flow table, your local forwarding table. So in software-defined networking, we change things so that each router contains a so-called flow table. A flow table kind of looks a little bit like a local forwarding table in that it defines out what port a particular datagram is going to go based on the destination address. But it does a little bit more than this. It allows you to have other types of control over the data that goes across your router. Now, this control is not just things like, okay, send out this port. It could also be to block traffic so that you can control where your traffic goes, i.e. your flows. It can be used to take certain actions, like inject packets someplace where you can set them aside for further analysis. So going back to the depiction of software-defined networking, we had a centralized controller, and that centralized controller could be a single machine or it could be a data center, and it can control things like routing, this global computation of all the best paths that your data flows should take. And that was called the control plane. Now, the control plane, when it makes or finishes its computation of the best paths, it then downloads the so-called flow table. It's called a flow table instead of forwarding table. It downloads that flow table into each router instance. And so that local flow table in SDN takes the place of the local forwarding table. And the local flow table has three entries. You can think of it as a specialized programmatic interface. If you specify a certain pattern, it controls different things or gives rise to different types of flow behavior or forwarding decision behavior for each one of these routers. So we have the packet header, and what this flow table consists of is three fields. One is called the header field. It allows you to match patterns for headers, so things like IP address ranges. It also has a counter section, which will tell you the number of datagrams that matched that pattern specified in the header section. And then it also has an action. What do you do when a particular aspect of the header that's encoded in the header field, when that matches? You can either drop a packet, you can forward a packet, or you can send a copy of it to the localized controller for further analysis. Okay, so let's take a look at this a little bit further. This SDN version of the data plane, the flow then is defined by the fields in the header portion of that localized flow table. And this implements what's called generalized forwarding. So now instead of just having very naive, you see a range of IP addresses, you send out a certain port, now you can have more fine-grained control about what in particular it's trying to match, not just to see if your IP address falls within a certain range. So you have this idea of a pattern, and with a pattern you can say a specific subnet or a specific host net number, or you can have a wildcard. And that wildcard said, well, this aspect of the header does not matter. So with this pattern, you can match values in the packet header fields. And when you get a match, okay, it'll perform an action. If it's not a match, it won't trigger that action. So what sort of actions can you have? You can drop a packet, not deliver at all. You can forward that packet out some port number. You can modify the packet. You can rewrite it. And when you're rewriting, you're implementing something that looks a lot like what a NAT is doing. You can also take a matched packet and send a copy of it or send it to the controller. So that way, it's, in essence, you're actively taking samples from your traffic and pushing it aside or sending it aside, setting it aside for analysis. You can also have priorities in your generalized match rule entry in your localized flow table. And what this priority does is it says, okay, well, if you have two patterns that will match on the same datagram header information, which one do you execute first? Because you can have some ambiguities. And then lastly, the counter tells you how many packets or how many bytes were matched. So you can collect those aggregate statistics to know how often certain rules or pattern matches were executed and which ones were executed. So the flow table in a particular router in SDN is computed by the centralized controller, and it's distributed also by the centralized controller. And it defines those behaviors that a router will engage in as it pertains to the so-called match plus action rules. On what criteria is it going to match header information for incoming datagram, and what action does it take in response when it gets a particular match. So here's an example. In example one, let's say you have a source IP address. So if you originate from a source IP address with subnet prefix 1.2, and the other two last 16 bits, least significant 16 bits, doesn't matter. So anything in that particular range of addresses that's destined for a certain destination subnet, drop that packet. Don't allow it to go through. Another one is if you have any source, it doesn't matter what the IP address, so it's wildcard, 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 going to a destination subnet which has a prefix of 3.4, so that means these last 16 bits can be anything, forward it out port 2. And lastly, if you originate at a single source IP address, so IP address 10.1.2.3, what is that? Well, that's a private domain. Regardless of the destination it's going to, you're going to send a copy, send it to the controller for analysis. So that's like saying, tell me all the traffic that's coming out of this particular host. I want to analyze it. Okay. So those are some example rules in the open flow table. So let's look a little bit more detail into what these actions and rules might be. So in the rules section, we have some bits here, and these fields represent certain patterns that we can specify associated with certain header fields in certain layers in the 5-layer internet stack. So we have link layer header information, the type of Ethernet, the media access controller MAC address for both the source and the destination, and that's unique address for your network card that they use to identify one another on the same network. And then you have a VLAN ID. A VLAN is a way of stitching together local area networks so that they appear like they're on the same network. And then you have a switch port. If you're a certain port that's originating that particular frame on the link layer, you can take certain decisions if you match certain aspects of these parts of the header information associated with the link layer. For the network layer, we have the source port, the destination, we have the source IP address, the destination IP address. We have the source port number. We have the destination port number. And then we also have the IP protocol, if it's TCP, if it's what version of IP. Well, we're using mostly Internet Protocol, but you can have different IP. Things on different platforms might specify different network layer, like Apple Talk and things like that. But nonetheless, if you have a certain source IP and destination IP, that's other patterns, specify blocks of addresses or singular addresses that you can specify in the flow table entry. You also have, for the transport layer, you can specify source and destination port numbers or ranges of numbers to impact the flow behavior. The actions, you can forward a packet out of port number. You can encapsulate it and forward to the controller. So that's the sending of that datagram to the controller for analysis. You can wholesale drop the packet. You can send it to the normal processing of looking at destination address ranges, or you can modify certain fields in certain ways. That's a rewriting, kind of having NAT-like behavior. Okay, so here are some examples. In this first example, you have what's called destination-based forwarding. Regardless of the source address in IP, if you're going to a certain destination address, 51.6.0.8, send it out port 6 on your router. Now, the next thing you can do with this flow is implement firewall behavior to block certain traffic. We have forwarding based on the destination, and we have firewall behavior. This firewall behavior says, if your destination port is port 22, drop the packet. Don't allow that traffic in. And so here you have two drastically different behaviors, regular routing behavior in this first example. You have firewall-like behavior in the second example, just by tinkering with different bits of this flow table's pattern matching section. So here, this last example, it says, do not forward datagrams, block them, that are sent by a particular host. So this person is not welcome. So here you have a source IP address, 128.119.1.1, and the action, when that source address is matched, the action is to drop those packets. Don't allow certain hosts to send. So for example, let's say you have a public network, like you're running a university or department, and you have people register their machines, and some machine, maybe someone is no longer part of the organization, you physically set up their flow tables to disallow that particular entity to send data. Or maybe there was some attack that was launched from a particular IP address. You might disallow that IP address to be able to send data, for example. Okay. So this other behavior is layer 2, switch-like behavior, and it deals with MAC addresses. So MAC address we'll learn when we talk about the link layer is a unique identifier for individual network cards on the same network, on the same subnet. And so here this says if you get a particular MAC address, and these are unique on your Ethernet cards, we're going to forward out port 3, right? And so here with the same flow table abstraction, you can get all sorts of diverse behaviors. You can get it to act like a router. You can get it to act like a firewall. You can get it to drop packets from a particular IP address. You can get it to act like a link layer to switch through a certain port number. So it's a very flexible construct, and the interesting part is you can influence these flows in one of these ways programmatically through a service-oriented architecture interface to the flow controller. Okay. So the OpenFlow abstraction is match plus action. You have a pattern that you match depending on patterns for certain pieces of information in the headers, for the link layer, for the network layer, for the transport layer, and then you have an action that results that's taken when you get a positive match. And so this match plus action uniquely identifies different types of device behavior, whether it's switch-like behavior, NAT-like behavior, router behavior, or firewall behavior. So what does router behavior do? Well, router says match the longest destination prefix for your IP address, and the action to take when that match occurs is to forward it out of a particular link. A switch says when I get a particular destination MAC address, when I match one, the action is to forward, which is called flooding, and we'll learn more about that when we deal with the link layer. The firewall behavior is when you match a particular IP address and port number, the action is either to permit this traffic to proceed or deny this traffic to drop those datagrams. So here it is, we can implement the behavior of arbitrary devices on the network by simply changing some of these bits in the match portion of the flow table, as well as the action portion in the flow table. And so, of course, NAT does rewriting. You look at an IP address, and the action is to rewrite the address and the port number. Okay, so here's an example. And in this example, we have a bunch of hosts, and we have host 5 here. We have host 6. Host 6 is here. So we have 5 and 6 served through this upper left-hand router. And in this, host 5 and 6 are going to be sending to host 3, H3, or H4 if it's going to send to H3 or H4 datagrams from host 5 or 6, rather than going directly to host 2 from their router or indirectly through the router. They're going to go indirectly through this router S1. Okay, so it means that they don't want to traverse this link. They want to traverse that link going down, not that link going down and to the right, your right. Okay, so how would we do this? Well, we set up a flow table. In this flow table, what we'd say is, okay, well, if the source IP address for this router here, the first router S3, and that's the flow table that would be installed in that router by the controller. If the source IP address is 10.3.***, so that means any IP address in this subnet attached to S3, to which S3 belongs, if you have any source address in that range, and it's trying to get to any destination address, 10.2.***, well, where are you going to forward? Out port 3. So that means any traffic associated with an address attached to this S3 is going to go this way, out port 3. Okay. So that takes care of the first hop, and now the second hop associated with the local flow table in this router S1 down and to the left. If the ingress port, and this is an interesting point, ingress port is the port number in which datagrams arrive. So it says if your ingress port is port 1 for the router, right, that's a link layer construct, and your source IP address is from the 10.3 subnet, and destination address is in the 10.2 subnet, you're going to forward out port 4. So that means all traffic that sources here and has a destination associated with this network reachable by S2, you're going to send out this port 4, right? So you're going to go this way. So this first flow table is going to send all that traffic down through link 3, and then the second flow table in router S1 is going to send all that traffic to the right out port 4 on router S1. Okay. So then lastly, we have the flow table for this last router, S2. So we have ingress port 2, so all data coming in port 2. If the destination is 10.2.0.3, meaning it's going to host H3, forwarded out port 3. Okay. This takes care of packets that are destined for H3. Likewise, if the ingress port is 2, okay, and the destination address is 10.2.0.4, send it out port 4. So with that, we can reach either host H3 or host H4. Okay. So with that, we finished up our module on the data plane, and with this, we will segue. Okay, so we're going to continue on with the control plane. And in our discussion of the control plane, we're going to look at more global decisions, where the forwarding plane talked about the local forwarding decision, and even with SDN, we can impact flows as it pertains to how traffic makes its way onto and off of a particular router. With the control plane, we look at a set of decisions in order to establish end-to-end paths. And so here we're going to understand principles behind the control plane. We're going to look at traditional routing algorithm as well as software-defined networking. And we'll also look at key protocols like Open Shortest Path First, BGP, Border Gateway Protocol, and so forth. Okay, so recall that in the network layer, layer 3, we had two major functions. One is called forwarding, and that's the moving or the switching of packets from input ports to the appropriate output port. And that was referred to collectively for all the routers across the network as the data plane. Now, when we shift gears for this chapter, we're going to talk about the control plane, which is the routing decision. That's the determination of the route taken by packets from some source host to some destination host. So that's going to consider a set of decisions, local forwarding decisions, for a set of routers all throughout your network in order to implement a certain path, and that's called the control plane, when you collect together all of those considerations across your network. Okay, so the routing determines the route taken by packets from your source to destination. That's your control plane, and there are two approaches how you might structure your control plane across the network. One is the traditional approach, that's per router. We have routing algorithms in each router, and they communicate with one another. And the other is to logically centralize it. That's where you have the controller, and each controller, through a control agent at each router, is going to collect information. It's going to perform computation at a centralized server or data center, and then it's going to take that result and use it to install a new local flow table in each one of the routers. So the flow table takes the place in SDN. It takes the place of the local forwarding table. Okay, so per router control plane. Well, we had our routers, and each router has a local forwarding table. We also have running in each router, and there's nothing special about a router. A router is just a host. Each router is going to run a routing algorithm. And these routing algorithms running in each router, they exchange information with neighbors that are running in routers that share some connection with another router. And that information contains traffic information, how much traffic is going along each link, because it knows how many datagrams are flowing along each link. And then it takes that information and uses it to determine what its switching decision should be in order to minimize some notional cost between paths from end to end. So once that is done, the routing algorithm halts and it installs a new local forwarding table that implements the forwarding, i.e. the association of certain IP address blocks or subnets to certain output ports. And then your routing is implemented in the data plane. That's the forwarding decision. And so here, collectively, the control plane consists of all the routing algorithms that talk to one another to collect information globally about the network's traffic conditions. And then the data plane is the set of local forwarding tables that have been installed at each of the routing nodes. And so with the logically centralized approach, again, you have these router processors. Instead of having individual routing algorithms, they have control agents. And these control agents act on behalf of a remote controller, which is a centralized server or a cluster or data center. And these control agents' job is to transmit information about local traffic conditions to the centralized controller, which then makes this global set of decisions about routes. And then the result of that is to push the forwarding tables down to the control agents that then install them into the respective routers. So in the direction of the control agents sending information to the remote controller, that's network and traffic information. Let me go back here and let me select my pen here. Again, let's select a pen color blue. So in the direction from your control agent pushing information to this remote controller, that's going to be traffic info information. And in the direction, opposite direction from the controller to the control agent, that's going to be the local flow table, right? So the control agent installs that flow table into the router to effect the switching decisions or the flow decisions. And the beautiful part about this that we talked about before is that the flow table can implement behaviors that act like a NAT, act like a traditional router, act like a firewall, or act like a switch. And so what that means is programmatically, if your server or your process interacts directly with this remote controller in some fashion through service-oriented architecture, before your computation that makes use of the network, before it runs, as a prerequisite, it can establish the way that data flows across the network to best suit that application. So you can have per application differences as to how the network's flows are set up to benefit that application. Okay, so the control plane consists of this remote controller and the computations it performs, and the data plane consists of this network of control agents, and they install local flow tables, or they send traffic information to the remote controller. And mind you, one of the pieces of information it can send is not just traffic information, but one of the actions that the local flow table can implement is to take a datagram, encapsulate it, and send a copy of that datagram to the remote controller for some sort of analysis on your packets. Analysis. Okay? All right. So let's take a look at some prerequisites that you need in order to implement these routing protocols. There are two major flavors of routing protocols, these global decisions. One's called link state, and one is called distance vector. Link state is more centralized, distance vector is decentralized, and the trade-off has to do with the rate of convergence. How soon does it settle down to a final answer? Well, link state converges faster, and we'll see why that is, than distance vector, but link state sends a lot more data across the network in order to gather those partial pieces of information that reflect what's happening traffic condition-wise across the entire network. Okay, so what is a routing protocol? The goal of a routing protocol is to determine so-called good paths, and good can mean many different things. And these paths are called routes, and it's the set of links you traverse, or hops, going from the sending host to the receiving host. And intermediate between the sender-receiver endpoints, you have a sequence of routers, each one of which stores and forwards this datagram along a path. And that path, therefore, consists of a sequence of routers that the packets will traverse when they're going from the source that originates it, ultimately arriving at the destination endpoint. And so good can mean many things when you talk about a good path. It can be the path that's the fastest. Well, that's always a good thing. Maybe it's the path that's least congested because, as we found with our discussion on transmission layer, if it's congested, well, eventually you're going to get timeouts and your end-to-end good put is going to be slower, right? It's going to be less. You could have the least cost path. You could associate a cost with a link, and that cost could actually translate to dollar value. If you have a choice between using a fiber optic link or using a satellite link, you'd prefer to use the fiber optic link because it physically, monetarily costs less to use a fiber link than it does a satellite. Moreover, if you're going to deal with routing and you get quite good with techniques for routing, you'll never be at a loss for a lot of employment. It's a top 10 challenge in networking because traffic conditions on a network will change, and the parameters that you set that influence your routing will dramatically either help your end-to-end throughput, your good put, or damage your end-to-end throughput. And there's a lot of high stakes involved because if you're a service provider for a network and you make a mistake, then everybody on your network thinks the problem is that Netflix is too slow when it's really this particular part of the service provider's network, someone made bad decisions on the routing policies. Okay, so how do we do this routing? Well, first we need a good mathematical abstraction, and the abstraction that is used for routing protocols is that of graphs. And the reason for that is because there are already a lot of well-defined algorithms in place that are good at determining paths along a graph. So we'll start out with a graph here. We have a graph here, and in this treatment, each node is used to represent a router. So you can think of each one of these alphabetic letters as being a router address. It doesn't matter what it is. It's just some address that identifies your router. So each node is a router, and you're going to have a source router, and you're going to have a destination router. And in truth, we have a local area network, and that router can reach that host, whether it's the source or the destination host. So here's the destination. Here's the source. So we talk about routers when we give our conversation about routing. So here, router U can reach this source. Router Z can reach that destination. So when we're establishing a pathway, we're looking how we can get a datagram from router U to router Z with the least amount of cost. Now, each one of the links, some of these links, that could be a satellite link, that could be a fiber optic link, this could be copper wire or coaxial cable link. Now, each link has this so-called decoration. It's a number, and that number represents the cost associated with that link, regardless of if cost is actual money or cost could be congestion, right? And so these decorations on the edges can certainly change over time because traffic conditions can also change over time. So we have a graph, and a graph is a mathematical construct in abstract algebra. So it's a mathematical structure, and it consists of two sets, N, the set of nodes, and E, the set of edges. So N is the nodes, and E is the set of edges. Now the set of nodes, those are your routers. So here we have router U, V, W, X, Y, and Z. So the set of routers for this example contains U, V, W, X, Y, and Z. So then we have the set of links. Now this set of links here, you'll notice we use this parenthesized expression. And here we have a tuple, and it's an ordered two-tuple. So if we have a particular node N1, comma, N2, that represents a link from node N1 to node N2. Now mathematically, the convention is that a link is unidirectional, right? And so when we use this parenthesized expression, it's called an ordered tuple. And so here, if it's not stated, you can assume, at least at this juncture, that if we have UV, that includes VU. But mathematically, when you have this parenthesized expression, typically it means that it's ordered. But in this case, the appearance of a link corresponds to what's called a bidirectional. So it's not a directional graph, it's an undirectional. No direction is implied by the node ordering. Okay? All right. So here we have what links? We have a set of links here. We have the link between nodes U and V, so that represents this link. We have a link between U and X that represents this link. Likewise, and I won't go through all of these, link between V and X that represents this link. So you'll also notice that each link has associated with it a number, i.e. a cost. So we're going to introduce a so-called cost function, but at this juncture, we're just going to talk about the structure, the set of nodes here, U, V, W, X, Y, Z, and the set of links where each link represents a communication link, and it doesn't matter if it's wireless, if it's wired, if it's fiber, or what have you. So this graph abstraction is a very useful thing. It's used in routing, among other things, because we have a lot of very sophisticated tools, clever tools that we can use. Once we translate the problem to a graph, we can now make use of these graph algorithms that will find for us what the optimal paths are. Okay, so let's introduce now this idea of a cost. Now, every link has a cost associated with it, and we depict that using the decorations, these numbers associated with each edge. So take, for example, this edge UV. That's the edge U, comma V, rather U, comma W, which is the same in this graph because it's not directional, of W, comma V. Now, the cost function, C, is going to take two parameters, the first parameter, the second parameter. These are both going to be nodes, right, or routers in our case. And that cost function is going to return back some number, and that number is going to be the cost of that link between, in this case, U and W, which is the same as W and U, because this is not a directional graph. So here, the cost of a link represents the cost associated with the edge, the decoration graphically, if we draw the graph. And the cost of a path, therefore, is going to be the cost of all the links that we traverse in getting from the source and the destination. So let's say the source along a path, you go from node X1 to X2, X2 to X3, X3 to X4, likewise up to XP minus 1 to XP, right? So we traverse a set of links, X1, comma X2. The next link would be X2 or edge, comma X3, up to and including that last link would be XP minus 1 for that last hop, XP. Now, if we were to compute the cost, you'd have the cost of this link plus the cost of that link plus the cost of that link, and we add them up, and that's the cost of an entire path. So let's take for an example, if we were going to have cost of a path, and let's say we have going from U to V, right? So that's going to be U to V, and let's say we said from V to W, that would be some V to W, and let's say we said from W to Z, right? That would be the link W, comma Z. Now, if we wanted to know the cost of this path, well, what's the cost of the path from U to Z using this set of links? That's just the cost of UV plus the cost of VW plus the cost of link WZ. So that would be 2 for the cost of link UV plus 3 for the cost of VW plus 5 for the cost of ZW, which would be equal to 10 for total cost. So now in a routing algorithm, what the ask is what is the least cost path, not the cost of any path, but what is the cost associated with, what is the, not the cost of any path, but what is the smallest cost path or the least cost path between a particular source node, in this case U, and a particular destination code, let's say Z. Well, just by looking at the graph, that would be from U to X, from X to Y, from Y to 2. So that would be from the path U, X, and then X to Y, and then Y to Z. So we take the cost from U to X, that's 1, plus the cost from X to Y, that's another 1, plus the cost of Y to Z, that's 2. So that total is going to be a path cost of 4. So you notice here, if we go from U to V, V to W, W to Z, that cost is 10. If we go from U to X, X to Y, Y to Z, that's a cost of 4. Now, this path along the bottom, U to X, X to Y, Y to Z, that's the so-called least cost path. And so if you're going to make a routing decision and you want to push a datagram from U to Z, where U is the source and Z is the destination, well, the least cost path, an optimal route, therefore, to take is along this path, down along the bottom. So that's what a routing decision is. And now we need a way to mechanize this, and we're going to make use of graph algorithms to mechanize that global consideration. But in order to make that global consideration, what we need is the cost of each path, the traffic conditions associated with every single link on our network. Okay? All right. So there are two classifications of routing algorithms that we have. One is called global or decentralized. And global, as the name implies, that all of this information about all of the link traffic state is going to be collected by every single router. So let's take, for example, router U. It's going to get information from V, it's going to get information from W, information from X, information from Y, information from Z, right? So every single router in the global case is going to send its copy of its local link information to every other router, right? And so each router is going to send its link state to everyone. When you send to everyone, that's called broadcasting. So you're going to send what's called a link state broadcast. And we saw with DHCP that you can broadcast using that specialized broadcast address. And in this case, you're going to be forwarding all this information across the network. Okay, so that's global. Decentralized means that you're only going to send locally to your neighbors. So locally to your neighbors means that V is only going to send to U, X, and W. U is only going to send to V, X, and that's it. W is only going to send to V, X, Y, and Z. You only send your link state information, called a distance vector, to your local neighbors, those routers with which or with whom you share a connection on the other side of the link. And so with global information, all the routers have complete information about the traffic status or the distances, and that's called the topology. That's the link cost information. So each router has complete link state information, and therefore the algorithms make use of it are called link state algorithms. In the decentralized version, that local information is called a distance vector. So your router only gets information about the physically connected neighboring links and the cost to those neighbors through those links. And it goes through an iterative process of exchanging information only with its neighbors. Now, eventually, if each router exchanges information with its neighbors, that information is going to wash its way across the network. But it's going to take longer to do so because your information hits my neighbor, my information hits your neighbor, all of a sudden things change, and then we have to continue that computation and that local exchange until eventually nothing changes. And that local link state information is called distance vector. Hence, you have what are called distance vector routing algorithms. And so the other classification of routing algorithms, we first talked about this global versus decentralized. It talks about how this link information or traffic information is propagated to other routers across the network. The other one is this routing algorithm static or dynamic? So static means that routes change slowly over time, right? You can produce a computation, you set your forwarding tables, and then the conditions on the routes changes very slowly. The other is so-called dynamic. Routes change more quickly. You have these periodic updates and things are always changing. There are drawbacks and benefits to both of them, and we will see more about why that is and the two major classifications, namely distance vector routing algorithm as well as link state routing algorithm. Okay, so with that, we will use this as a stopping point, and we'll continue back on Thursday. So I will see you all online on Thursday.